we will do a bit of revision today and we'll run through a notebook. We'll look at 5 or 6 different methods to get the decision surfaces in SVMs. We previously discussed that SVMs are popular binary classification techniques where we want to draw a separating hyperplane which maximizes the margin. The points lying on the margin are known as the support vectors. We only need these points in order to do our classification. We don't need any other points. Folks, please turn off your laptops. If your deadline is really urgent, if it's really important, you can sign your attendance and you can leave. But please don't use your laptops in the class. We discussed the notion of separating hyperplane with respect to the different dimensions. We can have 1D points for points in 1D as a hyperplane. When the points are in 2D, we can have a separating hyperplane as a line and a hyperplane in higher order dimensions, in high dimensions. So we looked at this question as to which hyperplane should we choose among these three, and we concluded the third one is the best because it maximizes the margin. We then defined the equation of a hyperplane. We said let's start with an origin. Let's have a plane, a point on the plane which is known to us x0 and any general point on the plane P, and we can then draw these vectors. We know the W vector is the perpendicular vector to the plane at point P0. We wrote the equation as W dot x plus B equal to 0. W and x are the same dimensional vectors. We then figured out the distance between two parallel hyperplanes because that's what we're saying is the margin, the distance between two parallel hyperplanes. Wx plus b1 equal to 0 and wx plus b2 equal to 0. We figured out that the distance between these two is b1 minus b2 divided by the magnitude of w vector, and you can just put an absolute value on the numerator also if you're just talking about the distance. So folks, I said just 2 minutes back, can you please turn off your laptops? If you want, you can sign and you can leave. We've talked about the two. In the formulation, we talk about a +1 and a -1, and I had hinted this in the previous class also that please expect some questions on this. If you were to change this +1 and -1 to +k and -k, and the equation of the separating hyperplanes as wx plus b equal to +1, wx equal to plus b equal to -1 to wx plus b equal to +k and -k, would you get the same answer, you get the same formulation or something else? We then calculated for these formulations that the margin is inversely proportional to the magnitude of the w vector. We said that our goal is to maximize the margin, but it's not just maximize the margin. What else do we need? We discussed that if you just maximize the margin, you could misclassify all the points. Right? I can have minimize the margin. I can have a w vector equal to 0. But that is not sufficient for us because our objective is to correctly classify all the points. So therefore, the constraints are that we correctly want to label all the points. So therefore, it becomes a constrained optimization problem, and we wrote this in a very succinct fashion. Yi w dot xi plus b greater than or equal to 1, where yi is either +1 or -1. So therefore, we get this quadratic program. We want to objective is to minimize the magnitude of the w vector subject to inequality constraints which are linear. We then took an example in 1D where we said that the dark blue point and the dark red point are going to be your support vectors because of these are the points which are closest to the separating hyperplane. Corresponding to the 4 inequalities, so each point introduces an inequality. Corresponding to each inequality, we made this graph where we looked at the direction of the origin and direction in which the inequality is feasible. We then looked at the overall feasible region, and we found out that the binding constraints or the constraints which take an active part in deciding the feasible region are the ones which are corresponding to the points which are closest to the separating hyperplane in this trivial case, and these correspond to w equal to 1. If you want to minimize the w in the feasible region, it is w equal to 1. We could have not chosen w equal to 2, 3, etc. We choose w equal to 1. Correspondingly, we get b equal to 0. Now, what we said is that we can also convert the primal to a dual form. There are a bunch of advantages, specifically when we introduce something known as kernel methods, kernelization or basis functions, where the dual formulation becomes very handy. We change the problem from minimize half the magnitude of double squared subject to linear constraints, linear inequalities, by introducing an alpha parameter for each inequality, where each inequality corresponds to each data point. So therefore it becomes half I equal to 1 to d wi squared, because w is a d-dimensional vector, and then corresponding to each inequality we add this, the second part of this objective. So this function, overall the Lagrangian function, is a function of w vector, b scalar, and n alpha values, where n alpha values correspond to the n points in the data set. We have the constraint that alpha I is greater than or equal to 0. So in constraint optimization, we have looked at the fact that for binding constraints, alpha I is greater than 0. For non-binding constraints, alpha I is 0. And then when we studied constraint optimization, we looked at the basic ways to figure out the derivatives with respect to the different quantities involved in this function. You find out the partial with respect to b, set it to 0, you get this condition, summation I equal to 1 to n, alpha I yi equal to 0. We've said that yi's are now positive ones and negative ones. And then when we found out the gradient with respect to the w vector, we can finally then write L of alpha as summation I equal to 1 to n of alpha I minus half, then you have this double for loop kind of a write-up, alpha I, alpha j, yi, yj, xi dot xj. So this xi dot xj is the most important part which I want you to concentrate on, and this is what we'll modify in the coming slides. So therefore what we've written is that minimizing w squared, or the magnitude of w, subject to linear constraints which are spoken directly in terms of y's and w's and b's, can be reformulated in the dual as maximizing L of alpha. So minimizing in the dual is equivalent to minimizing in the primal is equivalent to maximizing the dual, and correspondingly the constraints are also now changing. We also looked at the fact that we'll have for the support vectors we will have alpha I not equal to 0, and for non-support vectors I will have alpha I equal to 0. We took this example in 1D again, but this time in the primal. So I wrote this in terms of L of alpha, and by symmetry I wrote that this is the whole formulation, but by symmetry I wrote that alpha corresponding to the two x equal to 2 and x equal to minus 2, they will be zeros because these are not going to be support vectors, and the alpha corresponding to x1 and x1 equal to 1 and x1 equal to minus 1 have to be the same. Why? Why do the alpha corresponding to x equal to 1 and alpha corresponding to x equal to minus 1, why do they have to be same? Summation alpha I yi is equal to 0. For the alpha 1, we have y equal to 1. For alpha 3, we have y equal to minus 1. So therefore, if these two quantities, alpha 1 and alpha 3, have to sum up to 0, alpha 1 has to be equal to alpha 3, equal to the same alpha. Or you could have just said geometrically by symmetry, they'll be the same. So therefore, we have seen that we can just simplify this and write this as some function of alpha, 2 alpha minus 2 alpha squared. We minimize this with respect to alpha, and once we do that, then you can calculate the w vector to be summation I equal to 1 to n alpha I yi xi. Importantly, the only terms which you need to consider here are the support vectors. The non-support vectors are useless here because their alpha i's are 0. So therefore, whenever you have to calculate w, you only need to care about the support vectors, which is a much smaller, typically a much smaller set compared to the whole of the data set. And then we showed how we can calculate b. We know that yi wxi plus b minus 1 equal to 0. You pre-multiply both sides by y1, yi. We know that yi squared has to be 1 because yi is either plus 1 or minus 1, and when you multiply both these, you will get b equal to yi minus w into xi, and you calculate this for the support vectors. You can calculate B for every support vector and then you can just average it out. Okay, so now we will be looking at a notebook and we will try and see if we can formulate all of them, these methods, and make some predictions using the different variations we have seen. One, we have seen the primal. Second, we have seen the dual. Is the air conditioner working or no? No? Yes, no? Yes? Okay, at least for me it's not working, it seems. I have generated this very simple binary classification data set. I fit a linear SVM. Thus far, all the SVMs that we've been seeing are linear SVMs because we have not used any projection to high dimension. The previous lecture towards the end, I very briefly touched upon this topic. There is another important term, C equal to 1 E6. So I've kept it C to be a very large value. Does anyone know what C could be? So we discuss about C when we talk about soft margin SVMs. I had discussed very briefly in the previous lecture that if our data is not linearly classifiable, it's not linearly separable, we have two things which we could do. One, project the data to high dimension space where the data is linearly separable. Second, be okay with some points being not clearly visible, not on the correct side of the hyperplane. So therefore we have two methods. We will see both of them. So I've just I do model.fit x comma y. Now my sklearn implementation gives me model.dual coefficients. And these dual coefficients are minus 0.14, 0.11 and 0.03. But we just said a few minutes back that alpha E has to be, what is the condition for alpha E? Greater than or equal to 0. But here alpha E is, the first alpha is minus 0.14. So is sklearn's implementation wrong? Or have they done something smarter here? Any thoughts on what we are looking at? We just discussed that the alpha i's have to be non-negative. And here in sklearn's implementation, we are seeing that the first alpha is turning out to be negative. So what is wrong? I heard the right answer here, the first two benches. Can you speak out? You can make an educated guess. At this stage, you don't need to be 100% correct. So sum of these values seems to be correct. But previously, we had seen that summation alpha I yi is 0, not summation alpha I is 0. So therefore, perhaps what they have done is they have multiplied the alpha I with the corresponding yi value. So this is not really alpha I, this is alpha I into yi. Alpha I yi summation has to be 0, which you can see. One important reason they might have done is to directly encode the label of the class yi. So previously when I was, in the morning when I was trying to do alpha I into yi, and I was trying to show you that it should equate to 0, I was not getting 0. Could anyone guess why? One, so let's say if I take the absolute values of these now, but if I was doing summation alpha I yi, I was not getting equal to 0. Any guesses why? Sorry. No. So by default, what is the label that we give to the negative class? By default, not for SVMs. 0. In SVM, we have to specifically give it to be -1. So therefore, I had wrongly just given from my data, my y's were 0s and 1s. If I do 0 into 0.145 and 1 into 0.11 and 1 into 0.03, I don't get a 0. So therefore that convention is important. The negative class is -1, the positive class is +1, and the alphas that sklearn gives is just making it more convenient. So they have pre-multiplied with respect to the class label. Right? So now I get these values, and you can clearly see that summation alpha I yi has to be 0. I then also print my support vectors. My support vectors are vectors in the original space, in the 2D space, 9, -4, 8, -8, and 7, -8. You can see these points, 9, -4. 9, -4 should be this point. Let me just plot 9, -5, sorry. 9, -5 is this point, blue point. So there seems to be one blue point which is a support vector, and there seem to be two orange points which are the support vectors. They are 8, -8, 8, -8, and 7, -8, 7, -8. So these 2 points and this blue point are serving as the support vectors, and you can verify that for the first support vector, the alpha into yi is negative, which means that this is the -1 class. The other two are the +1 class. So thus far we've been able to get the alpha i's or alpha i's into yi's. So I'm just trying to simplify by saying that these are my actual alpha i's. Each of them have to be non-negative. And these are my support vectors. I can now plot my support vectors as I discussed. So these 3 points turn out to be my support vectors. I can then also look at, so I've shown you y, the y is my y vector. If I do index y by model.support, these are the indices of the support vectors. I get 0, 1, 1. The labels corresponding, the y is corresponding to the support vectors, but then I need to remap 0 to -1. So therefore I've done this. I've called this variable y -1 and +1, and wherever I have a 0, I'm replacing it with -1. At this stage, if I print this one out, I get -1, 1, 1, which is exactly what we had. Now, in theory, we had seen that the w vector can be written in terms of alphas as what? Can anyone tell me? What is the relationship between w and the alphas? Does anyone remember? In general, we can write w equal to summation I equal to 1 to n alpha I yi xi. So we've said that we are writing w as a weighted combination of xi, of all the points, but all the support vector points have non-negative alpha i's. For all of the other non-support vector points, alpha is exactly 0. So therefore, we can write the w vector just as I equal to 1 to number of support vectors. So we're just iterating over the support vectors. And that is what I'm showing you. So I've conveniently just written this as a form of a dot product. Alphas into ys -1 and +1. This just gives you alpha I yi. This gives you alpha I yi. And then model dot support vectors are dot product. So we take the dot product with them. And that's how you get the w vector. I'm just using the dot product to vectorize things. Otherwise, you could have written a for loop and got the same answer. So you should convince yourself that by using this dot product, we'll get the correct answer. Importantly, the w which we find using our calculations and the w which we get using model.coefficient, this is the sklearn's implementation which directly gives you the coefficients. They are exactly the same. There is some difference in the shapes, but let's ignore that for now. The values are exactly the same, which means that our method of starting with the duals, which is the alpha i's, and then going and calculating w is correct. Now we also looked at how to calculate the b value or the intercept. In the dual form, we sum the values of yi minus w dot xi for all the support vectors, and then we divide that by number of support vectors. If we do that, I am just, here I am explicitly writing it rather than using some vectored notation. I get the number of support vector points. I calculate B sum, I initialize it to 0. For each support vector point, I add ys, which is just yi minus w dot xi, where xi is a support vector. If I do that and I measure my answer, I get the exact same answer with respect to our own calculation and model.intercept given by sklearn. Right? So therefore, what we have confirmed thus far is that if we start from the duals, we can get the w's and b's. At least we can get them for the linear kernel. This is where you need to be more active and understand that why, if we do the same procedure for more complicated kernels, which we'll discuss, you will not be able to get the same answers. You will not be able to use exact same methods because of certain things which we'll discuss. Now, our aim here in this exercise is to be able to make plots like these, which show the margin, which show wx plus b equal to 1 and wx plus b equal to -1 lines. So we want to be able to show these, and for this we will use multiple methods. The first method which I want you to see is, I have just created this grid, mesh grid, by looking at 30 cross 30 points in this 2D space. I stack them up, and then my xy, what is the shape of xy? I have 30 points along the x-axis and 30 points along the y-axis. What is the shape of xy vector here? 300 or 900? 900 cross 2, because each point is a two-dimensional point and we have 900 such points. For each of such 900 points, I calculate xy. So I just calculate the dot product with w and I add b. So this is just w dot x plus b. If I do w dot x plus b, I get a z matrix. I just reshape it to the shape of x, and after that I'm just plotting these specific levels. The level where z equal to -1, z equal to 0 and z equal to 1 by different line styles, and then I'm able to get something like this. So what we did here was, we used a w vector which has been obtained by us via some fashion. You could either obtain w as model.coefficient, or you could use w equal to summation alpha I yi xi, and you get the same answers. And then you can finally calculate for any new point. The prediction is w dot x plus b. Right? So the first method is, once you have the w vector, you do w dot x plus b, and you calculate the z matrix, and then you just do a contour over that. The second method is, I want to use the fact that this line, I know the separating hyperplane has some equation. What is that equation? What is the equation of the separating hyperplane? wx plus b equal to 0. What is the equation of the above line? Okay, second last row in the orange t-shirt. What is the equation of the separating hyperplane? What is the equation of this line? Yes? See, if we are in the second lecture of SVMs and we can't answer this, we are not attending the class. Okay, it's the same row, the person in the white t-shirt. Yeah, second last row, person in the white t-shirt. What is the equation of this line, of this hyperplane? Okay, the person with the earphones on, the same row. There's only one with the earphone on in that row. Yes? Okay, last column, the person, second last person from the boundary. Yeah, that column. Second last row. The only person who's not looking at me and is now smiling. Yes. What is the equation of this line? Hyperplane. Okay, fourth row, middle column, purple. I don't know whether that's purple or what. W? Yeah, either Wx plus b equal to 1 or minus 1, we don't know that, but let's assume that this is the minus 1 class. So for folks who didn't answer, please try and pay more attention. This was the easy questions. We discussed this in the starting slide itself. So we know the equations of these three lines. What I'm then doing is I just get my x1 and x2 as again I just get my x coordinate, right? I can plot a line if I know it's y equal to mx plus c like form. So given wx plus b equal to 0, and here's the dot product, w dot x vector plus b scalar equal to 0. Can you tell me the equation of the line in y equal to mx plus c form? Can you work it out in your notebooks? So w is a vector, x is a vector. You can write w dot x to be w1 x1 plus w2 x2 plus b equal to 0. Then give me in the form of y equal to mx plus c, where y is the same as x2 dimension here. Are we passing the attendance? Has it reached? Where's the attendance? Okay, be quick with the attendance. Okay, does anyone have an answer? Well, let's calculate this. Take 30 more seconds. See, I think a lot of you are placing a lot of your belief in technology. I can tell you statistically that a lot of previous recordings have failed. So if you don't go through, if you're not active in the class and the recording fails, you'll not be in a good spot. And if you think that there are some previous recordings which I'd recorded and I'd covered the same material, you should be surprised to see that there are a lot of new things. Right? At least today's lecture, most of it we have never discussed earlier. Okay, what is the equation of the line in y equal to mx plus c form? Okay, the first column here and the lady in red. What is the equation of the line? Can we be louder? Okay. So I could still hear half only, but I'm assuming you were saying what is the correct line. We have w1 x1 plus w2 x2 plus b equal to 0. x2 is the same as y. So x2 is just minus w1 x1 minus b by w2. And you can write, this is what you need to write. So y equal to mx plus c, where m is minus w1 by w2 and my c is minus b over w2. If you have this equation of the line now, and I give you any values of x, can you plot can you plot y equal to mx plus c? We can do that. And we can do the same thing for the margins. Importantly, the equation of the margin is slightly different. w1 x1 plus w2 x2 plus b equal to plus 1 and equal to minus 1. But we use the same tricks and we write y as a function of x and then we plot them. We get the exact same lines, which is again giving us some more confidence in our implementation that we have correctly found out w vector and the b vector and we can match this intuition, right? So importantly, here we were calculating wx plus b for all the points in the grid, and in the grid then we were looking at the values which are minus 1, 0 and plus 1. In the second method, we are just directly plotting those three lines because we know their equations. In the third method, we use something known as a decision function in sklearn, which essentially gives us the same thing. So all we write is z equal to model decision function of xy and then just do the reshaping. This gives us the exact same answer. So we've this one, z equal to model decision function of xy, you could think is pretty much this z equal to np dot xy plus b. All of them, both of them should give you the exact same answer. Okay. Thus far we have looked at three simple methods, three different methods to plot the decision boundaries. Now we go on to the case which we had already discussed previously, but we'll go over it again to revise. We said that in examples like this, the data is not linearly separable. What should we do in such cases? What did we discuss in the previous lecture? We project the data to some high dimensional space where the data is linearly separable. So in this case, we said that let's transform it to some space x and x minus 1 whole squared. If we project all of those points, we can see that the data is linearly separable. Here the linear separating boundary is x minus 1 whole square equal to 5 over 2, which gives you these two lines as the locus of the hyperplane, x minus 1 whole square equal to 5 over 2, which is x equal to 1 plus minus root 5 over 2. So you get two lines which now are linearly able to separate the data in high-dimensional space. We then also looked at a very specific example here. The original data in R looked like this and in R2 looked like this, where we do a transformation phi of x, which is root 2x and x squared. And then this becomes our decision boundary. We will look at this example again in a few minutes, why we chose this weird looking root 2x and x square term. We also looked at this example in the previous lecture. And this is about the point where we stopped. So we said that the linear SVM, the objective is to maximize L of alpha, which is summation I equal to 1 to n, where n is the number of data points, minus half the double for loop, alpha I, alpha j, yi, yj, xi dot xj. If we have to transform the data to a high dimensional space, we replace all the xi dot xj's with first you transform xi to a phi of xi and xj to phi of xj, and then you do the dot product of the newly obtained projected vectors. Right? So you have the original vectors in some RD space, you transform those into some high dimensional space, and then you do the dot products in the high dimensional space. Everything else remains the same. The steps I'm repeating: compute phi of x, where phi is a mapping from some lower dimensional D to capital dimensional D. Compute the dot product over the capital RD space, and often the capital D is the dimension in which you're projecting is much greater than the original dimension, and both of these steps are very expensive. Whenever we talk about expensive, we are talking about the computational cost. After transformation, would the alphas change? Yes. So the first one is a linear kernel. The next one is some new transformation phi. Correspondingly, the alphas will change. But this was just to show that the formulation remains the same. The only thing which you have to vary is replace xi dot xj, which is a dot product in the lower dimensional space, with the transformed vectors and the dot product in high dimensional space. So this is where we have the most interesting part of SVMs, which is known as the kernel trick. The word kernel, you might have noticed, is very overloaded in computer science and electrical engineering. Where else have you heard the term kernel? Operating systems? Anywhere else? Okay, I'll leave that as an exercise. I won't ask this in the exam, but just try and figure out where you... Kernel density estimation, that kernel has a similar connotation to this. I was trying to ask if you have heard of any other connotation. Linear transformations? Okay, that I have not heard. So you can immediately understand when folks from maths are answering. Okay, the kernel trick, which is the whole crux of this lecture, is to say that phi xi dot phi xj is very expensive. We need to do something in order to make that less expensive. So we say that we compute a function k of xi and xj such that k of xi comma xj is equal to phi xi dot phi xj. So what we're saying is that we're trying to compute a function k, typically k we choose what is the kernel function, which gives us the output of the dot product of the transformed or the projected vectors. Right. And importantly, the kernel function contains the dot products, but in the original dimension space. Right, so it will look very magical, but we'll just take some concrete examples and we'll be able to derive these. But in the abstract terms, you're trying to learn a function which has mapping, which has dot products in the original dimension, and that gives us the answer which is equal to the transformed vectors dot product, which is obviously in the high dimensional space. So we looked at this example where phi of x was root 2x and x squared. This is the transformation. So if this is phi of x, can you tell me what is this kernel function which corresponds to this transformation? Whenever you're given such questions, write down the first formula regarding this, which is k of xi comma xj equal to phi of xi dot phi of xj. Xi and xj are 2 points in the original dimension space. You do a transformation. After that, you do the dot product, and then you're trying to see if there is a kernel function which has some dot product in the original dimension. So I want you to work this out on your own. Do discuss with your neighbors. This is the answer I want you to get. I want you to derive this. Or rather, let's start from this point. Let's start from this definition of a kernel. If this is the kernel, 1 plus xi dot xj whole squared minus 1, can you prove that this kernel maps the original data to a two-dimensional space, which is root 2x and x squared? Right? So all you need to do is to just expand out this and then try and write that in the form of phi of xi dot phi of xj. So Kishan is asking the question, minimizing half w squared subject to some linear constraints, that corresponds to maximization of L of alpha. That is just the primal dual formulation. Minimization of the primal is the equivalent to maximization of the dual. That is the relationship, and I told this previously also to a subset. I will not go into all the details of why the primal minimization is the maximization. There's some set of slides which I mentioned which will give you some hints. But beyond that, I think it's just out of the scope of this lecture. Okay, so can you expand out 1 plus xi dot xj minus 1? If you do this, how many are able to derive that this will indeed project to the phi of x which I've written? Okay, so about 5 to 10 people. Let's wait for one more minute. in the interest of time, I will show you the answer. You can expand out this to be 1 plus 2xi dot xj plus xi squared xj squared minus 1. The 1 plus 1 minus 1 get cancelled out. Finally, you can write this as 2xi dot xj plus xi squared xj squared, which now you're trying to separate this out or write this out as the product of, as the dot product of two vectors. So by symmetry, we can see that the first term is root 2 xi and xi squared, and the second term is root 2 xj and xj squared. If these are the two vectors and you do the dot product of them, you will get equivalent to 1 plus xi dot xj whole squared minus 1. So therefore, the first vector, which only contains xi terms, you can write as phi of xi, and the second vector, which only contains xj terms, you can write as phi of xj. So therefore, what we are saying is that by using this particular kernel function, which importantly contains the dot product in lower dimensional space. In this kernel function, the dot product is happening in the lower dimensional space. That is giving you an equivalent projection phi of xi, and which is in a high dimensional space. So therefore, the dot product after the projection into high dimensional space is approximated by a function of the original inputs and the dot products in the lower dimensional space. So I've said higher, lower dot product many times, but I hope you get the crux of this. Any questions on this? So now we need to understand why we said that the kernel trick is a very useful trick and it saves us a lot of computation. Let's go back to the original data set, x minus 0, 0, 1, 2, 3, and so on. Now let's transform it to a high dimensional space where the data becomes linearly separable. That transformation is x, root 2x, x squared, and y. So this is the original dimension x minus 1, 0, 1, 2, 3. We calculate this one new dimension, which is root 2x, another new dimension x squared. So if we apply this transformation and we do not use the kernel trick, first we find out phi of xi. How many multiplications does that require? We have an x1. We have to calculate phi of x1. How many calculations does that require? 2. The first calculation is root 2x and the second calculation is x squared. Similarly, phi of x2, how many calculations does it require? 2. Once you have calculated phi of xi and phi of xj, you have two vectors of length 2. Now you have to do a dot product of them. So therefore, you do root 2xi into root 2xj, one multiplication, x1 squared into x2 squared, another multiplication, and then one addition. So therefore, the total number of operations, let's assume each operation takes unit time, is 7 operations are needed, 7 unit operations are needed. Right? Now I want you to work out in notebooks. If instead we use the kernel trick and we used this kernel, then what is the total number of operations needed? With the expanded feature set, we need 7 operations. In the lower feature space, what is the number of operations needed? How many say 1? How many say 2? 3? 4? Okay, good. We do x1 into x2, one operation. The dot product because it's scalar, but here it just requires one operation. Add one operation, take the square, one operation, subtract one operation. So overall 4 operations are needed. Now contrast 4 and 7. And this was a very simple transformation, only to one dimensional space higher than the original dimension space. If we were to project to a much more higher dimensional space, we can see that the number of calculations required is significantly higher. Okay, question for all of you, can you solve this? The answer is there, but just try and solve this for your own satisfaction, confidence. Now your original input space is two-dimensional, x1 and x2 or x and y or whatever you want to call, and I have a kernel which is 1 plus xi xj the cube. So what space does that belong to? That is my question. Again, given a kernel, you would expand it out, and once you expand it out, you don't need to do the full expansion. You just need to know that there will be symmetric terms, and you can write it as a product of two vectors. You can carefully notice that when you're writing the cube of this kind of an expression, you would have terms which are orders degree 0, degree 1, degree 2, degree 3. Right? So degree 1 terms is just 1, degree 0 term is just 1, degree 2 terms will be x1, x2, degree 2 terms would be x1 squared, x2 squared, and then x1, x2, so on and so forth. Once you write all of them and you notice where the interactions are happening, you can write it as one vector which only contains xi, the other vector which only contains xj. You do the dot product, you'll be able to see it's a 10-dimensional problem, 10-dimensional high projection. So you've gone from 2-dimensional original space to 10-dimensional higher projected space. We come back to the reason why we use the dual form, because of kernels only. So the main reason, the main advantage we get by the dual form is when we want to apply kernels. The primal does not really allow for the kernel trick. Right? The primal always says W, you need to compute W, everything is in terms of W. Whereas in the dual, we are talking directly in terms of whenever we want to make a prediction using the dual form, so whenever we want to make the prediction using the dual, we write something like this. Y hat of a new test point is sine of summation of this quantity, which is done over the support vectors, alpha I yi xi dot x test plus b. Now, when the data is not linearly separable, we will replace xi dot x test with phi of xi dot phi of x test. But phi of xi dot phi of x test, we have just been discussing, is very expensive to do. Therefore, we replace phi of xi dot phi of x test with k of xi comma x test. So therefore, only the dual form allows us to write this formulation. The reason is that the dual form is expressed in terms of the dot products. Right? So what we're doing is we are replacing the projection and then the dot product in higher dimensions with a kernel function, which is present only in the dual form. In the primal, we don't have this formulation. Therefore, we extensively make use of the dual form in SVMs, especially when we are using kernels. If you're not using kernels, then it's not particularly relevant. Is everyone getting this? Why we need kernels and why we need kernels calculation via the dual, not in the primal. There are few commonly used kernels. The linear kernel, which is just the linear SVM or just the default SVM you've been seeing. Polynomial kernels of the form p plus xi dot x, x1 dot x2 raised to the power q. And perhaps the most commonly used one is the Gaussian kernel or the radial basis function kernel, which is e to the power minus gamma and then xi minus xj, the magnitude, you take the norm squared. Okay, so thus far, for some of these kernels, let's look at all the kernels we have seen thus far. Does this kernel involve dot product in the low dimension space? Xi dot xj, we can very clearly see. Does this kernel involve the dot product in a low dimensional space? Yes. Does the polynomial kernel involve the dot product in a low dimensional space? Yes. Does the RBF kernel have any dot product in the low dimensional space? No? Or yes? It has. Proof. Start with this. You also know the formula for e to the power x via Taylor series. Or maybe just for simplicity, for now let's assume X is a one-dimensional vector. Let's forget about Taylor series also. Let's assume X is a one-dimensional vector. So if I just expand out the squared term, I get x minus z whole square equal to x square minus 2xz plus z square. And if we substitute it back, we get terms like e to the power minus gamma x square, e to the power 2 gamma xz, e to the power minus gamma z squared. And then we have something which is a dot product of the original data points. Right? X dot z is occurring. Although I've simplified it, I'm just using a one-dimensional vector. You will get the same answer if you use it in a more general sense, where you just write, instead of directly these products and instead of expanding out my L2 norm as like this, you'll have to write x minus z transpose into x minus z, in that form you write. But essentially the thing is that you will be able to show that there is a dot product of the data in the original dimension space. We have previously seen that this kernel lied in the two-dimensional space. This kernel lied in a 10-dimensional space. Similarly, for linear kernel, polynomial kernel, we can do the expansion, we can get a sense of what dimensional space they lie in. My question to you is, what dimensional space does the RBF kernel lie in? Here you can use the Taylor series expansion of whatever you're seeing on the screen right now. So in Taylor series expansion, given any function, what are we trying to do? We are trying to approximate it as a sum of, or as a high dimensional polynomial, or sums of various degrees of the polynomial. And what is the limit to which we can go? Infinite. So therefore, can we think of the kernel function as writing e to the power minus gamma x minus z whole square, and for just univariate case, and trying to expand it out. Can you see that it is an infinite dimensional projection? You can have it in terms of various orders, and that goes till infinity. And that is the interesting aspect. So in this case, this trivial case, we computed the higher dimensional projection, which is just 2 dimension. We go from 1 dimension to 2 dimension. We can plot it, we can fix the line, and we can check what is happening. In this case, we start with a 2-dimensional point input. We project it to 10-dimensional space, which is still reasonably feasible. You can do the calculations in this 10-dimensional space. But in the case of RBF kernel, it lies in the infinite dimensional space, which means that, can you compute phi of xi? Can you compute phi of xi in dot phi of xj? No, because phi of xi lies in an infinite dimensional space. So does phi of xj. So therefore, using such infinite dimensional space, you cannot even think of projecting through the data, but you can instead use the kernel function, which is giving you the important result, which is the dot product in the high dimensional space, which is instead calculated by dot product as a function of the dot product in the lower dimensional space, which is kind of magical, as to we don't really care about the infinite dimensional space. We just care about the kernel evaluation. Sorry, with the polynomial kernel. The polynomial kernel transformation, like we took one example, that would depend on the original dimension, and then you just expand it out. For example, here the input was 2D. This is the polynomial kernel. You will get, in this case, you got a 10-dimensional. That is the transform dimension, which the kernel is representing. So the kernel is representing the dot products of the projected space. by doing the dot products in the lower dimensional space. Further questions on this? So another interpretation of all these kernel functions, you can think of it as they are just trying to encode the similarity between the points x and the points z. Because they're trying to encode the similarity, the closer the 2 points, you'd want the values to be higher. Right? They're more similar. So in this case, if x and z are exactly the same, what does the kernel function evaluate to? 1. If x and z are slightly different, it will turn out to be some value. Eventually, will it be 1 or lesser than 1? Lesser than 1? Right? So what we're trying to see is that the closer the x and y values are, the more similar they are, their kernel function will evaluate to something close to 1, depending on the ranges that we are given in the kernel functions. So therefore, we can also importantly think of kernel functions as trying to encode the similarity between the inputs. And that you can notice in various kinds of kernels, you'll see. They encode the similarity. But in RBF, it's more relevant. So another way to look at the interpretation of RBF is that we can see that it's of this form minus xi minus x minus xi squared. We can think of this as an equation of a circle in high dimensional space. So it's like a radial term, radial basis function. You can think of this as the radial component. We can think of summation alpha I yi as the activation. So for those who might have studied, let's say, eigenfaces, eigenvectors, or something similar, you might have noted that there is an activation component and there is a basis component. And you're trying to represent any new image as some activations of certain basis functions. So each image, let's say we have identified that out of the 240 students we are sitting in this classroom, maybe I can represent each of them as some combination of 4 or 5 faces. So let's say Kishan is phase 1 into point 1 plus phase 2 into point 3 plus phase 4 into point 4 and so on. Whereas someone else, let's say John, is phase 1 into point 9 plus phase 2 into point 7 and so on. So in those cases, the phase 1, phase 2, phase 3, phase 4, which we are specifying, we can talk in terms, we can tell them as the basis functions, which we say as enough to describe the data set, and the multipliers are the activation components. So therefore, in this setup, we call summation alpha I yi as the activation component, and the e to the power minus xi minus x minus xi squared as the basis component. You'll always have activation and basis go together. Now, we said that there is a notion of gamma associated with the RBF kernel. So I'm also saying that it is trying to encode the similarity or how far points influences in describing the other point. So if the value of gamma is low, then the contour which we are, the map which we are plotting, what we're saying is that for low gamma, x and xj, even if they are far, the kernel will evaluate to a high number. And if gamma value is very high, then only if x and xj are very close, then the kernel will evaluate to a high number. Otherwise, the kernel will evaluate to almost 0. So what we're saying is that given a point xj, if gamma is very high, then the kernel function evaluation will be 1 only very close to xj, whereas if the gamma value is low, then the kernel function evaluation of xj comma x will be 1 for a longer, for x which are even further away. And you can see that by just the definition of the RBF kernel. It's e to the power minus gamma and to the difference between them, so the norm of the difference between them. So we can again go back to the notebook that we are seeing and try and understand what it means to use the dual formulation with respect to now the kernels. So we had seen this simple example of 2D classification where we are using a linear kernel. In the first method, I had shown I am using W. I'm calculating W's as summation alpha I yi, and with respect to the support vector, I'm looking at the support vectors xi's, and I found out B. Second method, I just directly found the equations Wx plus B equal to 0. Third method, I use sklearn's decision function. The fourth method is if we had transformed the data to high-dimensional space, phi of xi and phi of xj. Because we are currently dealing with just linear data and linear SVM, we have not actually transformed the data to any high-dimensional space. So therefore, our phi linear is just return x, right? If we had instead done a phi polynomial, then it might have been return x, x squared, x cubed, something like that. But since we are just dealing with phi, with the linear kernel, phi of xi is just x. The reason I'm showing you the same is that I'm showing you we had the original input xy. We transformed that to a high dimensional space via this projection function. We also do the same thing. This is my test points. I do the same thing for my support vectors. I transform them to a high dimensional space. I show the calculated alphas, the b's. Then I run this loop. For each x test in my set of test points, I do my decision equal to alpha I into the support vector into x test. Is this correct, or should this be? No, this is correct, because this is x test. I should perhaps just call it phi of x test. Right. So for each transform, each projected point, test point, I can calculate this dot product in the high dimensional space. Right? Do you notice the dot product is happening in the high dimensional space? I have transformed my original input to my support vector into high dimensional space and my test point into high dimensional space, and then I do a dot product into the high dimensional space. Now instead of doing this phi I dot phi of x test, we can now look at the fifth method, where I just use the kernel function. Right? So I use the linear kernel, which is linear kernel of x1 dot x2 is just the dot product of x1 and x2, but we could have used any other kernel. The important thing I want to show here is that now I have my support vector in the original space, my test point in the original space. I pass them through my kernel function, which is then added to the alpha EY, whatever we're doing. The important thing here is that the dot products, because of the linear kernel, are happening only in the low dimensional space. So I want you to very carefully look at these two lines. 33rd line here. This is if we are projecting the data to a high dimensional space. You first project the data to high dimensional space, then do the dot products, and then use them in the calculation. Instead, if we want to use the kernel function, which is 25th line here, everything else remains the same, but we directly use the linear kernel's functions definition on the low dimensional input. Right here, the difference is not particularly visible, but instead, if we had, this is what I meant. If my phi is my projection operation, if that is an infinite dimensional, in the case of RBF, this we cannot compute. This method we cannot compute because that's an infinite dimensional space, whereas we can still compute with respect to the RBF kernel if we use the kernel trick. All I have to do is to replace the linear kernel definition with the RBF kernel definition, and I'm done. Any questions on this? So it's a topic which is very often confused. And the utility of the kernel trick is not often particularly clear. So therefore, I wanted to go a little slow today and also show these notebooks which can directly show in terms of lines of code which are changing. Now you have to go back, look at this notebook again, and see what will change if you were to use the RBF kernel here. I'll show the RBF kernel and the details in the next lecture, but this is where I think you should be very clear as to what the kernel trick is and what the utility it is giving. Any questions? The